Okay, so far we talk a lot about many cryptographic algorithms like symmetric key encryption algorithms, authenticated encryption algorithms, message authentication codes, or hash functions. Now we are moving on to a new topic called public key cryptography. Okay, so idea of public key cryptography is first introduced by Diffie and Hellman in 1976. It is based on using a trapdoor function f, which takes the input p and provides the output c. But we are going to ask the following properties from this function. So it should be a one-way function. So it should be easy to compute fx when you know x, so obtain the output y. But it should be hard to invert f. So when you are given the output y, it should be hard to find x. So as you can see, this is how we defined hash functions, right? Now we are actually moving on to something new here. The difference is that the output size is not fixed, as in the case of hash functions. Also, in the trapdoor function, we are going to add one more property to this one-way function. That is, in the trapdoor function, they are like one-way functions. Easy to compute fx when you know x. Hard to invert f without extra knowledge. But it is easy to find the inverse of f with an extra knowledge, called the trapdoor. So this is the main idea behind the trapdoor function. So with this help, Diffie and Hellman actually introduced how we can use public key cryptography in a scenario where the encryption key and decryption keys are different. And everybody should be able to learn the encryption key, but from the encryption key, it should be almost impossible to obtain the decryption key. Okay, so this was the idea, and in their paper, they gave this idea, but they didn't provide any encryption algorithm. Okay, RSA was one of the first to give such an idea, but Diffie and Hellman introduced this idea, but instead of giving an encryption algorithm, they introduced a key exchange algorithm, which is famously known as Diffie and Hellman key exchange, Diffie-Hellman key exchange. And due to this new ideas, actually they received ACM Turing Award in 2015, actually, which is a very late award because, you know, all the internet security almost depends on this, and, you know, they should be rewarded this award years ago. So let's give the main idea behind public key cryptography. So it has some, it actually solves some of our problems. For instance, one main task of public key cryptography is confidential message transmission. This is actually done by encryption and decryption. But we can also do this by using symmetric key cryptography, right? But in this scenario, we don't have to, you know, do the key exchange beforehand. It also solves the problem of authentication with the help of digital signatures. So in the encryption and decryption case, we will give examples like RSA or Algamon. In the digital signatures, we will talk about DSA, digital signature algorithm, or ECDSA, elliptic curve digital signature algorithm. Also, public key cryptography can be used for key exchange algorithms. So in this scenario, you can exchange the key of a symmetric key cryptosystem through an insecure channel. Okay, so we will talk about Diffie-Hellman key exchange here. So it is somewhat different than what we have seen in symmetric key cryptography. In order to talk about all of these algorithms, first we need to talk a little bit about algorithm types, and then I will briefly mention some algebra where we'll be talking about groups, rings, and fields. And after that, it will be easy for us to talk about discrete logarithm problem, then integer factorization, RSA, DSA, Algamon, and so on. So let's start with types of algorithm first. So let's give a brief definition for polynomial time algorithms. An algorithm to perform a computation is said to be a polynomial time algorithm if there exists an integer d such that the number of bit operations required to perform the algorithm with a k-bit input is O k to the power d. Here we are using the big O notation, so we are actually removing constants here. So this is how you measure the running time of an algorithm, and this one is called polynomial time if it is given something like this. So d can be an integer like 2 or 5 or something. On the contrary, we have exponential time algorithms, which will be a lot slower than polynomial time algorithms. So an exponential time algorithm has an estimate of big O notation with O e to the power ck, where k is the total input length and c a constant. So here we are using e, but of course it can be an integer like 2 or 3 and so on. Here we are concerned about the exponentiation here. So if your running time is in exponential, then when the input size increases, which is k, then your algorithm will be very slow, and maybe if you increase k, after some point on, you will not be able to compute this algorithm. Okay, that is not that much of a problem in the case of polynomial time algorithms. So let's give an example and see how an algorithm can be defined as an exponential time algorithm. So here let's talk about trial division. Our aim is to find the non-trivial factor of an odd integer n by trial division. In the future, because we will talk about integer factorization, and the hardness of this problem will be the base of RSA algorithm. But instead of coming up with a very clever idea, let's say that we are going to do a trial division. Idea is as follows. You are given an odd integer n. So you can just try one by one, starting from 3, if it divides this number. Okay, so you can start with 3. Of course, you don't need to check 4 because we said that the number is not an even integer, it is odd. So 3, 5, 7, and so on, until the square root of n, because if you try all of these numbers and none of them divides n, this would mean that n is actually a prime number, because if you are going to find the divisor that is larger than square root of n, then if you divide this n with that number, then the result should be something less than this one, which you should already found it beforehand. So this is why it is enough to check this range. Okay, so algorithm is as follows. You start with 3 and check if 3 divides n. If it does not, you go to 5 and check if 5 divides n, and so on and so forth. So let's define k as follows. N is the number that we are trying to find the divisor. So since we are going to talk about bits, let's define k equals to log 2n. So this is the number of bits this number has. Okay. Number of trials. We are going to do approximately square root of n many trials. Actually, square root of n divided by 2, but constants will not be important in the future. So let's say that we are going to try square root of n many numbers. So since k equals to log 2n, then this means that square root of n is something like 2 to the power k over 2. So we are going to do this many division operations, right? Because we are going to check if 3 divides n. And division of a k-bit integer with a k over 2-bit integer is of big O notation k square. So I haven't defined this, but actually in the book of Koblitz, this is explained in a very good way. But just believe me that dividing a k-bit integer with a k-bit integer or k over 2-bit integer is of O k square. So every division requires this many operations. So this is actually a polynomial time, right? But I'm going to do this many trials. So in total, my running time will be this multiplied with this. So in the big O notation, I'm going to perform 2 to the k over 2 times k square many operations. Since this part is exponential, trying to find the divisor in this way, it has a running time of exponential. It will be, yes, exponential. So this is a slow algorithm. Question is, can you better than this? Can you come up with a better way of checking if a number, if n as a non-trivial divisor? The answer is actually yes, and you can do better than this. So far, we don't know a way of doing it in polynomial time, but we know a way of doing it in a sub-exponential time. So it is between polynomial and exponential time. So for this reason, we need to define what the sub-exponential algorithm is. Okay. So the definition might look a little bit complicated, but it is not actually that hard. So assume that I define a function L with two inputs, gamma and C, and it is defined as big O notation, e to the c k to the power gamma multiplied by ln k to the power 1 minus gamma. So gamma here is is a real number between 0 and 1. C is just a constant larger than 0. If k is the input size of an algorithm, and if the estimate of the time cost of the algorithm is L gamma C with gamma between 0 and 1, the algorithm is called a sub-exponential time algorithm. So you might think that why we are defining it like this, because if you look closely, here I deliberately not choose gamma equals to 1 or 0, because if you choose gamma equals to 1, just put 1 to this definition, 1 minus 1 will be 0, and so on. So you will end up with e to the power ck, which is the definition of exponential time. But if you choose gamma equals to 0, this k cancels out. Then, you're going to have a ln k to the power 1, but just, ln is a logarithm to the base e. So, and this is the e. So you know that from mathematics courses, this would end up with OKC. So it turns out to be polynomial time. So this gamma actually determines how fast the algorithm will be. If it is close to 1, it will be slow. If it is close to 0, it will be faster, because it will be coming close and close to the polynomial time, running time. So this is how we define sub-exponential time algorithms. This will be important in the future, because for integer factorization, we have sub-exponential time algorithms. So this is why RSA keys will be larger than elliptic curve cryptographic algorithm keys. Okay, so this is why I'm defining beforehand. So before moving on, let's also talk about some types of problems. We are going to talk about decision problems and search problems. A decision problem is a problem whose solution or output is yes or no. So you are going to decide if the problem is, correct or not. A search problem is a problem whose solution can be more than yes or no. Okay, so let's give it an example. So given a number n larger than 0, factorize n. This problem is a search problem, because we are going to try to find the divisor of this number, right? But if I ask the question a different way and ask you if, when I give you n, ask you if n is prime, then this is a decision problem. You are going to say yes or no. You can easily see that if I solve the search problem, if I find the factorization of n, I can clearly say if it is prime or not. So search problem actually, also solves the decision problem. So question is, if I answer this question, but without doing less work than the search problem. So question is, can you say that the number is prime or not without factorizing it, without finding the factorization of it, without finding the non-trivial divisors of it? And intuitively, you will think that it is not the case, but unfortunately, the answer is yes. This decision problem can be solved without doing the search problem. So we have faster algorithms for this decision problem than the search problem. Okay. So it is very counterintuitive, but we will talk about it when we talk about integer factorization. Okay. So as you can see, I'm talking about problems here, because in the symmetric key cryptography, We tried to design algorithms and we tried to introduce diffusion and confusion, but we didn't have a mathematical way of, proving that they were secure, right? Here in the public key cryptography, we are trying to come up with problems which are hard, so that if we depend our security of a public key crypto system on this kind of hard problems, that we can have mathematical assurance that the algorithm is secure. This is somewhat different than the symmetric key encryption algorithm. So in symmetric keywords, some people refer to it as the magical word, because everything works fantastically, but we don't have any proof there. Here we are going to try to come up with proofs. Of course, here, when we say a problem is hard, most of the time, we are saying it because currently we don't have a, fast solution for it. But maybe in the future, some of these problems may not be considered as hard because somebody might come up with a polynomial time solution or something. So let's give a few examples which we can, which we see as hard problem. So one of them is integer factorization search problem. This problem is the problem of finding a non-trivial factor m of an integer n, or else determine that n is prime. So if we can solve this problem in a very fast way, you can actually break RSA, because whole RSA security depends on this hardness of this problem. We will see in the following hours, but RSA encryption algorithm starts with choosing two primes and multiplying them, and then giving the multiplication result to everybody without providing those two prime numbers. So if you can factorize that number and find those prime numbers, then you can break RSA. This is the whole security relying on this problem. So currently, as I said before, we have sub-exponential time algorithms, but we don't have a polynomial time algorithm yet. Another hard problem is the traveling salesman search problem. This is the task of finding shortest route that starts from a city A, passes through all cities on the salesman list, and return to A. So assume that you have a map, there are connected cities, and there are either distances or maybe the price of this route. So you are trying to come up with the shortest distance or the cheapest distance from A to, where travelers start from the city A, passes through all cities, and return to A, or cities that are in the salesman list. So another hard problem is the tree coloring search problem. This is the task of coloring vertices of a given map graph with just three colors, such that no two neighboring regions vertices have the same color. Okay, so this is also a hard problem. All right. So another question is the knapsack problem, which we are going to design a encryption algorithm by just focusing on that problem. So as you can see, our starting point in the public key cryptography to have a hard problem, because we are going to use it as a trapdoor, as in the case where I explained in the beginning of the course, where Diffie and Hellman introduced the concept of trapdoor functions. Because the person who chooses the key or designs the system would have an extra knowledge. In the case of RSA, those will be the two prime numbers that they chose at the beginning will be their trapdoor. So by using that information, they will be able to decrypt the encryption, but other people will not find that decryption key because they would not have that extra knowledge.